There's many surfaces or materials that we interact with on a daily basis that are hydrophobic. So raincoats, good example, Teflon surfaces in general, cookware even, like a Teflon coated frying pan. So this is where the water molecules prefer to be interacting with themselves as opposed to interacting with the surface. And what I do is manipulate polymers or plastic materials where I synthesize new ones or learn how to process them in a way to be able to create some sort of useful application or material as a result of the inquiry. So one of the things I'm especially interested in right now is in making superhydrophobic surfaces. To make a surface superhydrophobic, we need to take a combination of two things. The chemical properties are still really important, really necessary, and we have to combine those with an extreme surface roughness. So we take the hydrophobic material, form it into a series, an array of posts, or very extreme topography, and it's that combination of surface chemistry and topography that combine to keep the droplet suspended on the tips of the posts, such that the droplet's basically surrounded by air. It's almost a perfect sphere, and only maybe 1% of the surface under the droplet is actually in contact with the water. The practical applications of this technology could be in the medical area, where, for example, we want to transport a fluid like blood from one location to another, either to build it into a device for doing some type of test on small quantities of blood, or to make a device that helps people breathe more easily, as in for a blood oxygenator. So this would be to make a blood oxygenator, we'd want a device that's able to transport blood with the minimum amount of pressure to the minimum invasiveness so that we don't damage the blood in any way. So we'd want a surface that the blood could roll over very easily with very little friction. Also, we'd want a surface where the air or oxygen can permeate through the surface and be able to interact with the blood very easily. So we could oxygenate a lot of blood in a short amount of time. The real challenge is how do we make that surface such that it's also compatible with the blood. When blood interacts with most surfaces, especially ones that a synthetic surface, it finds that it doesn't know that surface well and starts depositing proteins and other chemicals from the blood onto the surface. And so it changes the surface from a well-controlled one to one that's covered with protein. And so we can lose the superhydrophobic properties as a result of this change. So what I'm studying is how to modify polymer surfaces in order to make them compatible with blood by using very specific types of polymers, and then how to take those types of polymers that are compatible with blood and create these extreme topographies that are necessary in order to keep them superhydrophobic. So making a biocompatible or blood-compatible superhydrophobic surface is really quite a challenge, but it's a really important application that I hope that I'll be able to succeed in my research at CSI.